Hello and welcome back to Fourier Transform, the video series where we talk about the special integral transformation that works for functions defined on Rn. And indeed, in today's part 28, we will restrict ourselves to a suitable subspace of integrable functions. This will be the so-called Schwartz space, which describes some special functions that are smooth and nice under the Fourier transform. But as always, before I give you the explicit definition, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And you should know that as a member on Patreon or Steady, you can download the additional material for the videos. And then without further ado, let's immediately go to our special function space, which we denote by a capital S. And behind it we just write the domain and the codomain, and as always we have Rn and C respectively. And you should know that we use the letter S here because it's named after the French mathematician Laurent Schwartz. And this is why in short we just call it the Schwartz space. And the most important fact for us here is that this one is a proper subspace of L1. First, this means that the Fourier transform is well defined for every function in this subspace, but we will also see that the Fourier transform acts nicely on this space. Indeed, here I can immediately sketch a typical graph of such a function. And there we have exactly two properties. On the one hand, it should be a smooth function, so C infinity, and on the other hand, it should be rapidly decreasing. This means the function goes fast enough to 0 when we tend to infinity. And this guarantees that the whole integral of the function exists. And in fact, rapidly decreasing here just means that it goes faster to 0 than any polynomial. So you see, we require much more here than just C infinity and integrability. However, soon we will see that this is exactly the correct requirement to guarantee that we don't leave the space when we apply the Fourier transform. But first, we should formulate the precise definition of the Schwartz space. And as already discussed, it should be a set of functions defined on Rn and with codomain C. And now let's write down the two conditions that we have discussed before. First, we can just say that f is in C infinity, which just means that all the partial derivatives of f exist. This means no matter which multi-index alpha you choose, d alpha f exists. And now what we actually want is that every such partial derivative is also rapidly decreasing. Therefore, the function should go faster to 0 at infinity than any polynomial. And in fact, we can estimate any polynomial by taking the standard Euclidean norm of x. There you just need to know, if we square this norm, we have a quadratic polynomial. And then a higher degree polynomial we just get with a natural number n as the next power. And now you see what we want is, regardless which n and alpha we choose here, we always want that this term goes to 0 when we send x to infinity. However, since x lies in Rn, it's simpler to just describe this limit process by a supremum. So we take the supremum of the absolute value here, and this one should be a finite number. Clearly this is always finite if we just consider a compact set, which means this guarantees that we have the behavior at infinity as we want it. So we simply say that this supremum is not equal to infinity. And as already mentioned, this should hold no matter which multi-index alpha we choose. And we can also make the degree of the polynomial as large as we want. So there we have it, this is the whole definition of the Schwartz space. And if you don't like this name, you can also say this is the space of rapidly decreasing functions. And moreover, please also note that there are different possibilities to describe the same behavior that we want here. This simply means you could also estimate with other polynomials here in the front if you think that's nicer. In the end, it's just important that we can increase the degree of the polynomial as much as we want. For example, it's also possible to avoid the supremum altogether if you bring this polynomial to the other side. This means you can describe a Schwartz function f by using normal estimates. More precisely, you would also say that you can change the degree with our capital N, and we also consider any multi-index alpha for getting our partial derivative, and then what we get is a constant c that holds for all the values of the partial derivative of f. the values are always below this constant c divided by the polynomial. And because of that, we don't want that the polynomial has the value 0 at all. Therefore, we just consider 1 plus the standard norm of x squared, and then to the power n as always. So this is the estimate that should hold for every x in Rn. Indeed, it's not so hard to show, but if you want, you can write down a proof for this equivalence. Nevertheless, you should also see that this inequality means that if we send x to infinity, then we go to 0 faster than any polynomial. So very well, and now I would say, let's bring this mathematical definition to life and let's look at some examples. And in fact, we already know a whole collection of Schwartz functions because we have the compactly supported C-infinity functions. Obviously, these C-infinity functions are also smooth and they go to 0 at infinity. More concretely, they are already exactly at 0 before infinity. Indeed, compactly supported means that the non-zero values can only lie inside a compact set. And the typical example you can see here in the sketch, this is a C-infinity function, but it's already equal to 0 outside of the unit ball. And otherwise, the values are given by this nice exponential function, which is smooth. And obviously this works in general. If you have a function f from CC given, then you can always choose a ball where the function is 0 outside. And if we have this, then it's also clear that we can satisfy the condition from above. Hence, let's simply write down the supremum from before, and then we immediately recognize that the maximal value we can have for our standard norm of x is given by this radius r. Simply because if we choose a vector that does not lie in the ball, the other term here will vanish and bring everything to 0. And this also tells us that for the estimate here, we can just take the supremum norm of this continuous function. This is definitely a finite number because it's the supremum norm over a compact set of a continuous function. In other words, the conclusion is that the whole thing here is always finite. So this shows what we have already expected. If we are already at the value 0 exactly, then we are definitely also rapidly decreasing. However, please note, this only works because we are also smooth in our CC infinity functions. This means that the indicator function from the last video is definitely not a Schwartz function. So maybe you could also say this one is also rapidly decreasing, but it's not smooth and therefore not a Schwartz function. This is important for us because we also want to deal with all the derivatives of the function as well. On the other hand, we could also have the opposite case where we are smooth enough but not rapidly decreasing. So for example, we could also take 1 over a polynomial. And maybe to keep it simple, let's formulate the polynomial with the Euclidean norm again. So here you see all the partial derivatives exist and they also go to 0 when we go to infinity. But the problem is simply, it's not fast enough in the decay. And in order to see this, we just have to take the capital N greater than this given m. And then we can do the multiplication as before, and we don't need any multi-index, we can choose it as 0 and take the function itself. And now if we send the norm of x to infinity, you see that the numerator grows faster than the denominator. Hence we are not bounded at all, we go to infinity here. So in short, polynomial decay is not fast enough. What we typically have for a Schwartz function is exponential decay. Therefore, we can just take the exponential function with a negative exponent. For example, we can take minus the norm of x squared in the exponent. And clearly, with the square here, we have the C-infinity property given. In fact, it's quite easy to show that all partial derivatives are given by the same function again times a polynomial. And since the exponential function is always faster in decaying than every polynomial, we have exactly what we wanted. This means whenever someone asks you about an example of a Schwartz function, you can just write this function down. It's a short formula and the behavior is easily explained with this sentence. And in fact, with the same reasoning now, you could take any function from the Schwartz space and just multiply it with a polynomial. Then this new function p times f is still C infinity and also still rapidly decreasing. Indeed, this follows immediately from the definition, because the degree of p can be as high as we want and we still have the same behavior at infinity. But most importantly, and in a similar way, you can also show that the Schwartz space is indeed a vector space. It's a complex vector space because scaling will not change the two properties we have for the function f, and you can also add two functions and you still get out a Schwartz function. So this is not hard to see, but we have even more because we can also multiply two Schwartz functions. And also there, the result is still a Schwartz function. Also there, I would say it's not hard to show because the C infinity property is still given, and because they are both rapidly decreasing, multiplying them should make the decay even faster. And now the second thing I want to write down also comes from the definition, because if f is a Schwartz function, we also know a lot about the partial derivatives as well. Namely, in the definition it's already stated that they are also rapidly decreasing. In other words, you cannot leave the Schwartz space with the partial derivatives. Okay, so these are natural properties we get for this nice space of functions. But as you already know, we want even more, because we want to apply the Fourier transform to S. And this is definitely possible because we have L1 functions here, but we get even more. Namely, the image of the Schwartz space under the Fourier transform lies in the Schwartz space S again. And this immediately implies, if we just consider the Schwartz space, then we can apply the Fourier transform as many times as we want. And we will see that repeating the Fourier transform is what we need when we want to define the inverse of the Fourier transform. But this topic is definitely something for the next video, so I really hope I meet you there again, and have a nice day. Bye bye.